In this video, we're going to talk a lot about volumes and all the different things that you could be asked on the AP exam. I'm not necessarily going to type any of these into my calculator or necessarily solve them. I'm mainly going to set up the integrals. Okay, so the first one, find the area of R. So I guess what we need first are the intersection points. So x equals 0 here, I think it'll be 0, 1 will be that intersection point. This other one is 1.904 comma 6.711. Okay, that's the other intersection point. So finding the area. Well, the area is simply the integral of the intersection, so we'll do it from x0 to 1.904 of the top function, which is the line, minus the bottom function, which is e to the x. And you would just do the antiderivative. You know, you'd say, okay, it's x plus 3 halves x squared minus e to the x, and you'd plug in the bounds. Right? Now, if it were rotated around the axis, okay, well, remember, every rotation, make a little note here, every rotation gives a circle, and we're trying to find the area of kind of the donut or the washer, the Cheerio, however you want to think about it. So we always, for every rotation, we're thinking pi times big radius squared minus little radius squared. And if you need help remembering that, go back, watch some videos on that. Like I said, this is just going to be kind of a quick review. So we're going to have pi integral from 0 to 1.904. The big radius would be given by the line, so it would be radius squared minus radius squared, and that would do it. Okay. Now, if I were going to rotate around the y-axis, well, the minute you start rotating around something that's vertical, then we need to change our equations to be x equals equations. So let me just kind of do that over here. We'd have y minus 1 divided by 3 would be equal to x. And this one, of course, would be x, that's equal to x, not 3. This would be that x is equal to the natural log of y. So rotating around this axis this way, we're always, you know, we usually say top minus bottom, but what we're really saying is what function is furthest away and makes the biggest radius from the point of that we're rotating around, from the axis of rotation. Well, the natural log is going to be the larger radius. So we got a couple of things we have to do here. We're still going to have pi, it's still a circle, but our bounds are now going to be y's, so from 1 to 6.711. Our equations are now in terms of y, so natural log y squared minus the other radius squared, and we're doing dy, like that. Okay. Now, if we were to rotate around the line y equals negative 2, well, y equals negative 2 is down here. So what we did then was the radius, you know, the line used to give me the radius. It's how far off the axis I am. But now I've made the radius 2 units larger. So I'm going to have pi. We're back to rotating around a horizontal, so it's going to go back to 0 to 1.904. The big radius is going to be 1 plus 3x plus 2. And I know I could simplify it, I just wanted to kind of show that plus 2 at the end. And the other radius would be e to the x plus 2. Okay. Now rotating around the line y equals 7. So now we're rotating around something that is above, you know, up here. So we need to find the difference between 7 and the functions to tell me what the radius is. So 0 to 1.904. We're going to have 7 minus the function. Now, when we rotate around something above, you know, again, we're always, what sets the outside radius is the function that's furthest away from the axis of rotation. In this case, that is e to the x. So there is my way of rotating around 7. Now, rotating around the line x equals -2. So now the vertical. So we're back to using like what we did in part C, using this. And of course, natural log, the y minus 1 over 3 tells me how far away from the axis I am. So if I'm rotating around -2, I made the radius 2 units larger. So we're going to have natural log of y plus 2. Like that. And that's it. Now again, this is a lot of information. There's a lot of stuff in here. But if you're having any problems, go back, watch some older videos that kind of are showing how to start. I'm just kind of running through all the different things we might need to know in volumes. So same functions, but this time we're going to talk about cross sections. Okay, so let me start drawing on this. If I think about squares, right, a square is base times base, so the area is base squared. If I think about a semicircle is, the area is 1/2 pi r squared. And a rectangle where the height is twice the width, so base and 2 times base, so the area is 2b squared. Okay, now cross section's perpendicular to the x-axis. So if I draw that, if I can bring this up here for a second. Like that. So let's start with a square. So this means you are putting little squares right like this. Okay. So the way you get the base is simply by finding out how far apart the two functions are. And then to get the volume, we integrate it. So you remember the base, or the bounds went from 1 to 1.904. And it's going to be top function minus bottom function squared. And that's going to give me the area, or the volume, if those cross sections were squares. Now, if instead of squares they were semicircles, so now we're little semicircles like this, well, now the difference between the two functions is the diameter. So to get the radius, we need to take that difference and divide it by 2. So I'm going to have 1/2 pi. I'm still going to have an integral. And the difference between the two, 1 plus 3x minus e to the x, needs to be divided by 2 to get me the radius. Okay, so let me just show that one more time. I've got that 1/2 pi because it's a semicircle, and the difference between the two functions, I divide by 2 to get me the radius. Okay, and finally, if I'm doing this with the rectangles, the base is still the difference between the two functions. So I'd be able to integrate 0 to 1.904. And I'd have 1 plus 3x minus e to the x squared. But I'd have to put a 2 out front because it's 2 times base squared. Okay. Now the next one, find the volume I did the same exact thing, except now they're perpendicular to the y-axis. So maybe instead of doing them all, let's just talk about what would need to be different. Okay, the y-axis. So we would need to do dy. So we would need two x equals equations. We'd need this, like that. We'd need new bounds. We'd need to go from 1 to whatever that other bound was, 6.711. Okay, but other than that, the shapes would be the exact same. So, instead the squares would look like that. So the difference between them would be the natural log of y minus the line, and that would give you the squares. The semicircles, you take that difference and divide it by 2 to get you the radius. So the ideas are the same, and again, maybe in the interest of time, I won't necessarily do the whole thing, but make sure those changes are done, that you switch to dy, that you're using natural log. Finally, the region R is the base of a solid. For each cross-section, the area is that. Find the volume. Now, this is a little bit different, but I want you to think about this. To do volume, what we've always done has been to integrate the area of cross-section. That's what we've always done. Up here, we found the area of a square, and we integrated it. Here we found the area of a semicircle, and we integrated it. Here we found the area of the rectangle, and we integrated it. On the previous slide, we found the area of the circle, and we integrated it. Well, here we've been given the area. This is the area. So the volume must simply be the integral of that area. Like that. And we could actually do that one by hand, but this is the big idea. To get volume, we just integrate the area of the cross-section.